All right, so for this class, we want to see how we answer questions like this. And here, the question is very straightforward. They want us to complete the free body diagram for the entire structure. Now, it's important to understand which parts they mean. And here they're saying for the entire structure. And they actually go on to label exactly what they mean when they say entire structure. You see that in the question that follows, they have highlighted the pieces, but this time it's not the entire structure, it's only sections or parts of that structure. So in the first part, we're going for the full structure. So let's highlight where the structure starts and where the structure ends. The question starts first with ABC, and ABC runs from here all the way up to here. Okay, so that didn't come out well. Let's redraw that. So this highlights A, B, C, but then it continues. It also includes D and E. D is here, E is here. So if we were to include those 2 points, now we have this. Let's just control this. Okay, so this is our structure now to include D and E. So now this is what we have. So this is one piece. So we're not going to look at them separately for now. We're going to treat this as one piece. We have our point A here, and then we have our point B here, point C, point D, and point E. So I'll keep this, and then I want it for later. Now, what is happening here? So now we want, since we're doing a free body diagram, we want to remove everything that is attached to this. And in place of those attachments, we want to replace them by their respective effect on our structure. Now, let's start with all the ropes that are present on our structure. Now, if you recall from our previous class, whenever you have a rope that is attached to the structure, the resulting force that will act along that rope will always be such that it acts away from our structure. So it acts as if it's pulling on our structure. So here we have one rope. So the force due to this rope will have to be a force that goes in this direction, pulling away from our structure. So we can label this rope as tension 1. So everything has to be labeled. You're going to give it an assignment. So should we have to find it, we know exactly what assignment we get. Now, in this case, we have this rope continues and it comes all the way up to this side. So it attaches to point D here. So at point D, the same force will now act in this way. So at point D, it will now act in that way. So here, what you have to see is that because this is the same rope, the tension along or inside this rope is the same. But the only thing is that its effect to point A is such that it's pulling point A upwards in that manner. But its effect on point D is such that it's pulling point D downwards in that manner. So again, just don't forget, the tension in a rope will act such that it points away from the object, but it always acts along the direction of along the dimension of the rope. So in other words, the tension acting at D here along that rope will have the same value as our assigned T1 here. So that part has been sorted. Now I can finish up this side. Of course, you still have the applied force here, so I won't leave out what is already there. So we'll still keep this. And this has been given as 1,200 pounds. We're drawing a free body diagram here. So what is important are the forces. You can include the lengths as well, but the key here are the forces. So we have a weight that is hanging to this, but we don't want to show the weight. Instead, we are only drawing our structure A, B, C, D, E. But at this point, we have a rope that connects to our weight. So again, going by the same statement we pointed out earlier, wherever we have a rope, we'll remove it. But in place of it, we'll respond with a force that acts along the rope, pointing away from our object along the rope. So here, what will be the force, the magnitude of the force along this rope? You can label it T2, but really you don't want to label T2. Why? Because T2 then can easily be found when you conserve the concept of equilibrium down here. You have to see that the amount of tension T2 will actually be equal to the weight of the load down here. So instead of writing T2, we might as well just write the force there. So the force along this rope is going to be 3,600 pounds. So this is what we have done so far. Now let me just show you how our free body diagram so far looks like. We still have a lot to do, but so far this is what we have. We still have a few points that we have to touch on, and that includes to what is happening at E, what is happening at C, and I think we haven't finished sorting out what is happening at D. So let's finish up with those. So we're back to this point where we are adding everything. So when you are writing this in a test or in an exam, you don't have the ability to do this, of course. This is just software and tech. That's why I'm able to do all this. But for you, what you're drawing is a sketch. They don't expect you to draw something perfect. So you can just make a rough sketch. So if I was doing this, basically just draw a big enough line like this and a big enough line like this. And then now start pointing, oh, okay, here I have a force that goes like this. I have a force that goes like this. I have a force that goes like that. Just want to make these big enough so that at least someone can relate. But if you can still make shapes and then do this, do that. You have another one here, and then do this. Of course, you get how it goes. So let's continue. We've sorted out a few of these forces, and we continue sorting them out. So next up, we have point D. We notice that point D has ropes attached to two of its ends. So you have this part, the one going towards A, and then you have this part, the one going towards C there. So we have those two. So based on that, we want to also remove this rope here, acting from D towards C. But in as much as we can remove it by saying that we have this, and then pointing it in that direction, of course, away from the object, make this smaller. Do that away from the object. In as much as I can label it as T2. Here you want to ask yourself, do we have a connection between T1 and T2 there? So by connection, what do I mean? You see, this is a rope and it's coming down like this. As long as it is the same rope, we expect it that the tension along that rope will somehow be connected. I'm using the term somehow instead of exactly the same, because later on, as we study in this course, you'll notice that in some cases, a pulley in a system will actually affect or vary the tension this side from the tension the other side in the same rope. But for now, we are looking at this course or this topic before introducing that concept. So for now, the argument is that this support here or this pulley there does not change the tension that is in the rope here. But if you wanted to be careful, then what you would do here is label them separately to say the tension here is different to the tension here, but just indicate to say that if at point D, we do not have any losses, any friction, then you expect that T2 will exactly be the same as T1. Again, for this topic, when you're learning it before learning friction in CEE, the most probable cause or the most probable continuation here would be that T1 and T2 are the same. So I might as well label T1, T2 also as T1. So in other words, the tension this side will be exactly the same as the tension the other side. There'll be no effect due to a frictionless pulley there. So this means that we have now dealt with the point D completely. So we have removed the two supports, the rope this side and the rope this side, have removed them and replaced them by their effect on the structure. Now we move on to point C. For point C, we have ropes there as well. One rope going towards D, one rope going towards F. So again, the force inside the rope will always go away from the structure. So this one will go down. And notice that here it's the same scenario as earlier. Here, we're taking it that this pulley here or the support is frictionless, implying that it doesn't change the tension up and the tension down, prompting us to say that here, this will still be T1. And even up here, this will still be T1. So basically, this is what we're working with. So at this point, we are now done with everything on point C. So the only thing that we are now left with is point E down here, because at point E, we are also seeing a support. So again, I'm repeating that point. If you want to be extra careful, you might label or say that this tension is different from this. But if D here or the pulley there is frictionless, then we expect that the two will be the same. By frictionless, we mean if that pulley there, you can tell to something that is circular. If the pulley there can rotate freely, then it means that it is frictionless. We can assume it is frictionless. But if it's something rigid, meaning that maybe it is stuck in a way, it implies that it will vary the tension one side to the tension on the other end. So meaning that in such a case where this is rigid, then T1 and the tension here will be different, meaning I'll be forced to put this as a T2. If I took that route, this one would also be T2 here, but this one down here, if this is also rigid, then this has to be different. I'd go with T3. But here we're saying we haven't yet looked at rigid bodies or pulleys with friction. Because of that, we will assume this is actually free to rotate, same here. So we're going with this as the OT1s. Okay, so basically this is how we're approaching this. So we have now sorted out everything else except point E at the bottom. Now for point E, what type of support is this? The question doesn't say much, so we have to analyze our structure. So look at this, and let me just move everything else. So look at that type of support, and what do you guys think? We saw the types of supports we expect to find in this course. That support which is at point E, is it a pinned support? Is it a fixed support? Is it maybe a rocker? What are we looking at there? Can you guys say something? What do we think?
It is a support.
Yes, that looks like a fixed support. So this looks like a fixed support unless if the question said otherwise. So we'll take it as a fixed support. And when we're dealing with a fixed support, what do we expect? A fixed support prevents the object, or at this point, if this was fixed, it means that it can't move sideways. It can't go to the right, it can't go to the left. So put a reaction to say it reacts in a certain direction to prevent sideways motion. Apart from that, this point would not be able to go up or go down. So I can say that, okay, we expect that we would have maybe one vertical reaction as well to prevent vertical motion. Now, the direction of these forces it's a matter of guessing work. You can analyze the structure and try to predict that, okay, yeah, this is trying to fall in this direction. So a reaction is must be such that it prevents the fall. Like, for example, here, you can guess that because of this force that is down here, the more probable situation is that this maybe is trying to swing, falling forward like this. So the reaction at this point will maybe be such that it glues this thing to the ground. So maybe you'd say that I expect a reaction that will point down, but still it's an expectation. It's not something that is completely true or obvious. You can only ascertain that this, yes, is the correct orientation after the calculation. So here we're going to place the vertical reaction. I'll point it down. And then for the horizontal reaction, I'll predict or guess that it is going this side. I might be wrong, but again, we get it. So we need to label these, don't just put line. So I can label that this is the reaction in the Y, and this is going to be E in the X. But being a pin support, this one prevents rotation as well. So if you are dealing with a pin support, then we expect that there will be a reaction to rotation. So not a pin, a fixed support. So a fixed support also prevents rotation. So what do? We expect that at this support, there will be a reaction to rotation. So I can do this and say that reaction will come out in form of a moment, a couple moment. In doing this, we have now accounted for all the forces. So you can now just include the distances that are present so that now our final solution will look like this. So let's take this somewhere free. So this becomes our free body diagram. Of course, just add a few lengths there so that you are extra careful. Okay, Kondoni, you've got your hand up.
Yes, sorry, that was a mistake.
Oh, right. Okay, so this is what we end up submitting, unless if there are any reactions to this.
Yes, but now I do have one.
Right, go ahead.
Would there be another changing force from F going upwards apart from the one going down?
Okay, from F. So let's see where F is. F is here. So all you want to ask yourself is F part of the structure we're analyzing? And what is the structure we're analyzing? So see that? Is F part of what we're looking at? F is not. So our analysis ended somewhere here. It does not include this point. Have you got that, Condon?
Yes, I have.
Okay. So this is why the first thing I said is you need to understand your parameters. What are you finding? Which structure are you getting a free body diagram for? To help you get a clear picture on this point, let's do B. B now, you see, when you're looking at the free body diagram, I could have looked at this structure as a whole. When you look at this structure as a whole, you don't see what is inside. What is inside this rope would not be seen. It wouldn't come out as a force. You don't use or look at internal forces. When you're just looking at it as a whole system, you are only looking at external forces. So when you're using those principles of equilibrium, you're only looking at external forces. So for a structure like this, and then you're trying to conserve equilibrium, the only external forces would be this one here. Of course, now you'd have to remove here. You'd say that you have this one, and then you'd also have to say that at this point you have a rope. So you can also say, okay, this rope perhaps ends somewhere, and maybe put one that goes down. Those would be maybe what you would show at this point to say that is what you have. Debatable on whether you can show what is there in that rope. Of course, it is acting on the structure, so you might as well want to place that on as well at that point. But you are only dealing with the internal force, the external forces. Why am I bringing that point up? For one simple reason. When we were analyzing the structure A, B, C, D, we had this point here. This point, as you can see, it is some form of a connection between our structure or the structure A, B, C and the structure that's D, E. So that point B is exactly midway, or not exactly midway. It's a connection, or it's something that is between the two structures. So at this point, we might have a connection. It might be a pin, it might be a fixed connection, but we know to say wherever we have a connection, we will have forces here and there being present. But when this structure is being looked at as a full system, when the structure A, B, C, D, E is being looked at as one unit, the forces at that connection did not show up. Why? Because at that point, they were internal forces. So in drawing a free body diagram, we do not show internal forces. In fact, even somewhere here, there are internal forces. As you will see, when you start looking at topics that are coming ahead. But we don't show forces that are here because they are internal forces. We are only interested in the external. But in part B, now look at what they're saying. Assume that the joint B is actually a pin. So assume that this is a pin connection, pinning ABC and DBE together. So if that is a pin, what are they saying? Now they're saying draw a complete free body diagram for the member ABC. Now it's like they are separating the two members ABC and the member DBE. So when you separate the members, what was hidden now comes out. So what was once the internal forces there, due to separation, now that has to show up as an external force. So what happens? So look at what happens when I get the member ABC. So for the member ABC, I only capture it up to here. Okay, got the wrong one. So I'll get the member ABC, copy it up to somewhere there. I have separated the member ABC from the member DBE. But you have to be mindful of what this implies, because if the whole system was in equilibrium, then it means that even when you separate them, the individual pieces must still remain in equilibrium. So first, I'll account for what was already external. These two were acting at point C, so I'll still include them to point C. So these two were at C. So I'll still place them there at C. So let me just draw this one better here. But we have, this is T1 here. But we have at point B is somewhere here. So to our structure, let's say point B is somewhere here. This is where B is. Now B is common on both A, B, C and D, B, E. So it has to show up on both. Now, what we're doing here is we're now looking at one member at a time. So we have dismembered our structure so that we analyze what is happening to one member at a time. But even as we look at these members, they should still conserve the ideas of equilibrium. They should still be in equilibrium. What does that mean? You see, initially, the forces at point B were not showing up in our free body diagram. Why? Because in a way, they were adding up to 0. So the forces at this point were adding up to 0. So when we now remove, this is a pin, point number 1. Now, for a pin, what happens? What type of reactions do we expect? So if you have a pinned connection, a pinned support, we expect reactions to prevent motion sideways or along the axis of whatever you're looking at. So expect a reaction in the x-axis, we expect a reaction in the y-axis. So either vertical or as in either up or down or left or right, but we expect a reaction in each axis. If this is 3-dimensional, then we would expect a reaction even in the third dimension. But for this case, we're looking at only 2 dimensions. So we expect one sideways and then one vertical. Now what happens? Here it is completely up to you. Of course, the question says we're starting with A, B, C. So let's include these first on A, B, C. So on A, B, C, where are we going to choose our reaction to be? Again, completely up to us. So here, I will assume the horizontal one goes sideways like this. And I'll say this is B in the x-axis. For B in the y, again, here I am just assuming I'll pick B in the y to be this direction. Once you have selected the orientation of Bx and By, when you now move, by the way, just by doing this, our free body diagram is complete for the member ABC. This was the only point which was shared. But when it comes to the other piece, notice that this other piece has the same point we are from describing, that shared point. It is actually shared between the two structures and between ABC and DBE. That's the common point. Now what happens? You see, your decision in the previous case will affect how this one is supposed to be positioned. What do I mean? You see, when you bring these two pieces together, it has to be such that at that point B, the forces must still sum up to 0. So when you're now placing the reactions at point B here, this is to a pin, but now we're looking at this pin to the member DBE. So the reactions here will basically have the same magnitude as what you selected when analyzing the first separation you made. So if to the member ABC, I chose BY to go up, then to the member DBE, BY will have to point down. If to the member ABC, I chose BX to go to the left, then to the member DBE, the same BX has to point to the right. This is necessary so that when this is now taken back to make that complete setup we started with, the forces at that particular point must add up to 0. And clearly, notice that now when you look at this point, if BX is going to the left and another BX is going to the right, clearly in the X, we see that we get a 0. In the same way, we have BY going up, BY going down. Again, they cancel up, taking us back to this setup where at the point B, we had 0 as the external force there. So that is the whole logic there. So based on that, our solution here, when we dismember these two structures or these two members, this is how they are going to appear. Again, the selection here is up to you. I could have chosen this one, BY to go down and BX to go like this, meaning that here I'd have been forced to do this and do that. So when you're starting, it's up to you what you're choosing. You can choose anything. But once you make your choice, you must stick to that choice because your selection here affects how everything else is going to be. So that is the key thing you have to remember here. The minute I chose BY to go up, I had no choice. This side, the same force had to point down. Okay, so this is how we do this. And let's see, does this question continue? Now, the second part was drawing a free body diagram for DBE, which we have done. Okay, any questions up to here? Any reactions?